Hi there. I'm Rick Wessel, the Associate Dean for Academic and Student Affairs, and I'll be guiding us through this morning's session. This is just to give you an overview of the school as a whole before you go to the main event and learn about the specific department that you're thinking about studying in. I want to begin by introducing the dean of our school. Jayati Murthy came to UCLA in January and is the 7th dean in the school's 70-year history. She most recently was chair of the Mechanical Engineering Department at the University of Texas at Austin. Prior to that, she served as a professor at Purdue University and Carnegie Mellon University. Because of her time spent living in West Lafayette, Indiana, and Pittsburgh, Pennsylvania, she really appreciates the Southern California sunshine. She also spent a decade in industry developing computational fluid dynamic software for Fluent, a leading company in the field. While at UT Austin, she served as director of PRISM, the Center for the Prediction of Reliability, Integrity, and Survivability of Microsystems, a $21 million center of excellence supported by the National Nuclear Security Administration. But that wasn't risky enough, so she came to us. She brought tremendous energy to the school since taking the helm in January. She's implementing an ambitious plan to grow the school by 50 faculty positions over the next few years. And from your perspective, this is going to ensure a steady stream of new professors who can provide expanded course offerings while you are with us. She's also focused like a laser on identifying and implementing any changes that can improve the experience of our students. Please welcome Dean Jayati Murthy.
Thank you, Rick. Good morning, everyone. On behalf of the Henry Samueli School of Engineering and Applied Science, welcome to UCLA. I'm absolutely delighted to see you here. For those of you who were at Bruin Day yesterday, welcome back. Now, I want to start off by congratulating you on your admission to this amazing university. I don't know if you know our statistics. I was telling some of you yesterday, and I'll repeat them here again. This year, we had 22,500 applicants, not into UCLA, into UCLA Engineering. And this fall, we'll take less than 800 students. So that's how selective our process is. And you've been selected through this extraordinary competition. So you must be extraordinarily good. And so congratulations to all of you. And of course, the credit doesn't just go to the students, it goes to the parents as well, because you must have done something right to produce this extraordinary student that you have here with us. So congratulations to you as well. All right, so how many of you have completed your SIRs? Show of hands, please. All right, how many of you are thinking about it? All right, so I hope we will make the sale today. I hope everything that you see today will convince you to come to UCLA, because UCLA is a truly extraordinary place, and UCLA Engineering is absolutely amazing. So let me tell you a little bit about the kinds of things that you'll do here. First of all, we've got our amazing programs, 7 departments, all extraordinarily good and highly ranked. And so you will undergo a rigorous training program, at the end of which you're going to be very, very proud of yourself. So there's that. Then there are the clubs. UCLA Engineering is very big on clubs, and people do very significant hands-on projects in these clubs and teach themselves how to be really good engineers, and you're going to enjoy that as well. There are very good internship programs. Now, sitting here in Southern California, you are surrounded by industry, defense industry, software industries, all kinds of employment opportunities and internship opportunities that you will take advantage of as you proceed in our programs. There are opportunities for research as well, undergraduate research with our staff faculty, and all of that is going to be available to you. So what you will get in UCLA is a rich experience, both in the classroom and outside the classroom. And when you come to UCLA, it's not just UCLA Engineering alone. You are embedded in a university which has extraordinary richness of all kinds, right? First, there's the medical school right across the street, really a world-class medical institution which interacts with engineering every single day. So you are tied to real human problems, to the solution of these problems through creative engineering. We have a terrific management school, and many of our students will take courses there as well. So you come out rounded as both a manager and an engineer. We have a wonderful law school, and many of our students will go off to careers in law after a strong grounding in engineering. And then there are the performing arts, there are the visual arts. You are embedded in a school that is tightly connected to the entertainment industry and to the art industry. So if you have interests of that kind, UCLA is a terrific campus to play all of that out. And then there's the fact of LA itself. UCLA sits in one of the major global cities in the world, and there's the extraordinary richness of the city itself. Its enormous art scene, its enormous tech scene, the entrepreneurship scene that's all building in UCLA, and as an engineer, you'll have access to all of those riches. So your life here is going to be very full. I can tell you that engineering is not easy, all right? It's a serious profession, and at the end of it, you will emerge as a serious professional, right? And it will be challenging, you will work hard, but by the end of it, I'll tell you, you're going to be extraordinarily proud of what you will have achieved and what you will have learned here at UCLA. So welcome to UCLA, welcome to UCLA Engineering, and I hope you have an extraordinarily productive day here. So welcome again.
Well, this is an engineering meeting after all, so I think we need some graphs. Erky, can you pull up that chart about, yeah, so I just threw Erky a little curveball here, but there is this chart that we have a lot of fun looking at that shows back one from this one. We'll look at this in a second. Well, since this is up here, let me just explain this chart. This is really fun. This is how much money you make when you graduate. And the orange dots are engineers, and the blue dots are arts and humanities. And the x-axis is quality of school. And a lot of you guys have gone through this really arduous process of trying, and I know some parents take this very seriously. I've got a junior. You're trying to get in the best darn school you can, and that is your goal. But the truth is, in terms of outcome, you've already made the more important decision of choosing a really great major. And actually, your outcome as a person actually isn't as dependent on the school as it is on the fact that you're going to be an engineer, which is really cool, and solve people's problems. Of course, so you can relax and go to school where you want. It's going to be okay. And of course, if you do that, UCLA is obviously the right choice. Got a great beach, fabulous restaurants, excellent sports teams, as well as the best faculty and students that you could get anywhere. So it's the complete package. But if you do, but I have to say there's room in the world for any profession. And if you change your mind, and actually the smallest percentage of any university who come into engineering programs change their mind out of our program. But if you do, we've got the best programs in any other major too, so that's fine. But let's take a look at that admissions chart. Yeah, so this is what's been going on at UCLA admissions over the last, almost 25 years. And what you can see is that the number of applicants has grown. I call that an exponential curve. The blue lines. The red lines are the people that we can enroll, and that hasn't really changed. And that's why, as Dean Murthy said, wow, you guys really went through, you went through the eye of the needle to get admitted here because we have so many people who want to participate in our programs, and just a small number of seats. The really cool thing is that thanks to pressure from the state of California and pressure from the School of Engineering, we were able this year to change our target, which has been 650 for the last 10 years, to 750. So we're bringing in 100 more freshmen, or we're desiring to bring in 100 more freshmen this year than we have in past years. Actually, last year, 100 more came than 650 anyway, but that was just because more people are deciding to take our offers than ever before because it's just such a good program. So before you go on and see the department that is going to be your initial major, and you can change your major, we're going to take you through a tour of the departments because many of you might be interested in learning what exactly is engineering, what all of our departments do. And so we're going to have our chairs take you through each department. And we're going to start with Professor Jim Liao. So Professor Liao is so good at running departments that we put him in charge of two. And not only is he a great leader of departments, but he also is a great researcher. He's a member of the National Academy of Engineering and the National Academy of Sciences, and he's won the Presidential Green Chemistry Award, and then the White House kind of fell in love with him, and they also gave him the White House Champions of Change Award. He does a lot of work related to biofuels, just a lot of great chemistry work, as well as being a great leader of departments. So, Jim, to you.
Thank you, Rick. First, I'd like to join our dean to welcome everyone to UCLA and congratulate all the students and parents for doing such a good job in bringing up your kids, and hopefully you'll continue to do a good job in making the right decision. So, let's talk about our first department, bioengineering. So bioengineering is a discipline that applies engineering techniques and principles to biological and medical systems. In UCLA, our department is focusing on medical systems. Okay, if you go to a hospital, hopefully not too often, you'll see a lot of instruments, the EKG, MRI, PET, or those three-letter word instruments. Who built those? Those are engineering products. Okay, so use those engineering techniques, build those instruments that allow doctors to do diagnosis. Now, previously, these doctors and engineers are completely working in different segments. Now, more and more engineers are working with medical professionals, okay, to design a better, more interactive, and even smaller instrument. Now you can even swallow an instrument into your gut. Okay, sooner or later, you'll tell your parents, "Mom, I swallowed a camera." That's colonoscopy. Okay. If you're old enough, then you know that if you can swallow a camera into your gut, that's very useful. Now, just swallowing a camera doesn't do anything. You need to collect the data. I need to gather the information. You need to analyze the information so you know how your tissue, how every organism, not organism, how every organ in your body is functioning. And that requires engineering analysis. Okay, that requires data processing. Not only that, you need to compare this data with your DNA sequence, with the medical history, with the family history. Eventually, we'll get to the personalized medicine. And that requires individualized attention to every individual. And that requires a lot of collaborative work between engineers, life scientists, and medical doctors. So that's allow us now, as a field, we begin to be able to make blind people see again, paralyzed people walk again. These are the futures of bioengineering. And UCLA, we provide a very comprehensive curriculum. Not only give you a very good education at the undergraduate level, but because we have a wonderful medical school, we have a very large number of excellent faculty in life sciences and engineering that allow students to interact with. Many students, almost all students at undergraduate participate in some kind of research. So this is the bioengineering department. Okay, let's switch gear to chemical and biomolecular engineering. Okay, so now you can recognize that the name of this department also has some bio, so let's address that issue first. Okay. Why we also have another department focusing on bio? Because bio area is so large, okay, that requires so many different type of education. In chemical engineering, traditionally, the job is to convert some kind of resource to some kind of product. The resources chemical engineers used to use are oil, natural gas, and so on and so forth. More recently, chemical engineers has begun to use silicon or even some biomaterials, biomass or CO2 even, okay, to make products. And those kind of resources converting to product use a common type of processes. Next, please. Key. Okay. These processes look very different from outside, but in fact, the underlying principles have a lot of commonalities. And that's why students can learn the commonalities and then can be applied to making fuels and chemicals, applied to making materials, or even pharmaceuticals. That's where we group all the different different applications into one discipline. So what kind of products will you make? Okay, you can make fuels and chemicals, or the water bottle. Many of you probably have a water bottle with you. Those are made with chemicals. And not just chemicals. In the next generation, hopefully in 10 years, all these chemicals will come from renewable resources, either biomass or even CO2. All the bottle that you drink will be biodegradable. Okay, so those are the jobs of chemical and biomolecular engineers. And of course, very few people will realize that your favorite machine, cell phone, is actually manufactured primarily by chemical engineers. Intel, Motorola, Samsung, TSMC, those companies have more engineers than any other engineers in most cases. And then, of course, these kind of processes can be applied to make next generation pharmaceuticals. Okay? And these pharmaceuticals not just require a lot of manufacturing processes, but also scientists and engineers need to learn how these molecules interact with human bodies. So those are the kind of discipline that you will learn. In UCLA, we have a unique program that allows students to specialize in different options. For those of you who are interested in chemical and biomolecular engineering, you'll learn about that in the next hour. Thank you.
Thanks a lot, Jim. Now, I'd like to just mention, for those of you that are interested in bioengineering or in any of the engineering majors but want to have a biology bent, when you're looking at schools, it's important to realize that having a nearby medical school is a real edge. And something you have to realize is that for a university to have a medical school, they have to have a hospital, and to have a hospital, they have to have patients. So a lot of great universities have to have their medical school somewhere else where there are enough patients. UCLA, actually LA is big enough to have a hospital, as well as the great restaurants. And so we can accommodate, we have one of the best medical schools in the country, and between us and the medical school is just parking lot 9. In fact, when my first son was about to be born, we had to spend a lot of time in the hospital, and I actually lived in the hospital and would walk in the morning across parking structure 9 to go to work. So I'm very familiar with it. But anyway, that's an advantage that's important to consider when you're thinking about bio. All right, so next up, civil and environmental engineering. So Professor Jonathan Stewart recently received the UCLA Distinguished Teaching Award. A lot of our professors win this UCLA award. We pay a lot of attention to teaching. This year, though, Professor Stewart won the William B. Joyner Lecture Award for outstanding earth science contributions to the theory and practice of earthquake engineering, together with demonstrated skills of communication at the interface of earthquake science and earthquake engineering. So here to tell you about civil and environmental engineering is a guy who really knows how to shake things up, Jonathan Stewart.
Thank you, Rick. So I'm here representing Civil and Environmental Engineering. This is the department that deals with issues related to infrastructure. By infrastructure, I'm talking about the physical systems that essentially enable modern life in an urban environment like here in Los Angeles. The slides behind have kind of 3 rows of images which are depicting different elements of our research and educational programs in civil and environmental engineering. At the top, you have several examples of infrastructure, including water systems. So an interesting fact you may not be aware of is we're importing 60% of our water into Los Angeles and Southern California more broadly. It's coming through aqueducts, coming hundreds of miles. And every one of those aqueducts cross the same fault, which could rupture in a single earthquake, the San Andreas Fault. Other examples of infrastructure are our buildings. We've had some ordinances in Los Angeles requiring retrofit of buildings. It's recognized as a major threat to human life and industry. We also have transportation structures as part of our infrastructure, like the bridge you see. So all of these are elements of infrastructure systems that are essential for our society. They are all facing serious threats. So earthquake is one. The image in the top middle is the level of ground shaking with hotter colors indicating stronger shaking from a San Andreas Fault rupture. And we've been part of teams leading risk assessment procedures for that event. But in addition to earthquakes, we have, of course, climate change, sea level rise, changing weather patterns, and likely coastal flooding that comes along with these sorts of things. So that's another risk that our infrastructure faces. So what we're teaching students here is how to assess these risks, determine how they're likely to affect the infrastructure, with the objective of working towards a more resilient infrastructure framework for our society. Moving down to the second, that's the Sustainable Urban Systems thrust area for our department. So what this means is, we've always taught students, the traditional way of teaching students about civil engineering is you want to provide a certain degree of functionality, and you want to do so at a competitive price point. So these are the major considerations. But as we start thinking about sustainability, we want to do that while providing proper environmental stewardship. And so there are several examples of this that you can learn about as an undergraduate at UCLA. One is Netzero Buildings. So Netzero Buildings are a type of structure where they're not a net draw on energy resources. They're actually generating the energy, and in some cases even the water, that they need to operate. Another is related to CO2. So a lot of people don't realize that carbon dioxide, which is of course causing global warming, a large fraction of the human-induced carbon dioxide emissions is from the production of cement, Portland cement, used in infrastructure. So instead of contributing to the problem, we're working on on solutions to the problem where our structures are actually consumers of CO2 instead of generators of CO2 as a result of innovative materials used in their construction. Working your way across the line there, we have underway now, we're in the early stages of really a transformation in our transportation systems. We are headed, whether we like it or not, towards autonomous vehicles. This is an opportunity to really rethink how our transportation systems work. With autonomous vehicles, cars can be a lot closer together, basically. And that's going to change how we conceptualize our intersections, our freeways, and our department wants to be on the cusp of making that happen. Not to mention the fact that we're also in a period of increasing urbanization. And the way people get around is different. Increased use of mass transit as opposed to people driving solo in vehicles in from the suburbs. So all of these are part of going towards a more sustainable infrastructure. Moving down, we have water security. So one thing that's especially important in Southern California, as I've already mentioned, is we're completely dependent on massive import systems to bring our water in. That's been the case since William Mulholland back in the 1910s. And this is an infrastructure that is highly threatened. Climate change is drying up many of those water sources. And as I've already mentioned, each one of the aqueducts coming into Southern California can be ruptured by a single event. In order to address this problem, and we are in the lead on doing this with partners at water agencies and the state in California, in order to address this, we need to understand these risks. We need to be thinking about the hydrological cycle, how it's changing with time. And also, we need to be thinking about innovative ways to treat the water. We can be making much more use of our groundwater. We can be using our wastewater more effectively and reduce the reliance on imported water. So our students are learning about these sorts of things and doing the research that enables these technologies to be brought forth as well. So with all of these infrastructure issues, they exist within a framework that we recognize in a clear-eyed way is extremely challenging on the national level. If you Google ASCE infrastructure report card, ASCE is American Society of Civil Engineers, you'll see that our last grade as a nation is D+. That's D, by the way. This is a grade probably none of you have ever seen in your life, but it does exist. Trust me. So that is from 2013. That's horrible, right? And that's the state of our infrastructure. This is the underpinnings of our economy, of our livelihood. So that's a pretty sorry state of affairs. You would think that given that that is our reality, that we would be making a major national investment in improving that infrastructure, and of course you would be wrong. We spend 1.6% of our GDP on infrastructure investment in the United States, 1.6%, and that number has been in decline since the 1950s. Just for comparison, that number is about 5% on average in Europe and about 9% in China, which are some of our major competitors in the global marketplace. So we understand the infrastructure landscape is a challenge. It is. But it also requires engineers who understand the sorts of issues I've just hinted at here and who can operate within that framework in an effective manner. And that's exactly what we're doing with our educational programs and also, of course, with our research, which is addressing the most significant issues facing infrastructure in California and the US today. Needless to say, our students don't have any difficulty finding jobs. Almost all of them, unless they choose not to, get internships in industry with government agencies, utilities, while they're students, and they're highly sought after once they graduate, both in industry, with utilities, government agencies, and of course many go on to graduate school. So I look forward to seeing you in our departmental session. Thank you.
Well, thank you very much, Professor Stewart. Next up, the most popular majors in the School of Engineering, computer science and engineering. The computer science department is chaired by Professor Mario Jolla. As you know, UCLA is the birthplace of the internet. Professor Jolla was there at the birth. As a graduate student at UCLA, he was part of the team that worked on the early ARPA network system and protocols under the guidance of Professor Leonard Kleinrock. More recently, he has led the ONR Minuteman project designing the next generation scalable airborne internet for tactical and homeland defense scenarios. So here to tell you about what's going on in the computer science department is Professor Mario Jolla.
Thank you, Rick. So good morning to all of you, and thank you for coming at such early hour in such large numbers. I want to congratulate you again for the admission, and of course, now that you have admitted, you have choices, and I want to convince you that UCLA is an excellent choice, in particular because in our department, because you've grown so much that we are now engaged in aggressive hiring of faculty, both teaching faculty and research faculty. So when you come in, you'll be received by skilled faculty and also TAs They'll carry you through the first 2 years. You'll become accomplished programmers. And then you'll be ready to solve some of the problems you outlined here. So the number of these, all of these vignettes correspond to labs we have in our department, and also to upper division courses. So you'll be learning what the computer scientists and engineers do in real life. But we think that that is not enough, you know. You also should get some hands-on experience. In fact, besides being the chair, I'm also an undergraduate student advisor. So, and I enjoy that because that gives me keep in touch with what the undergraduate students really are aspiring for. And recently, there have been more and more requests to get involved in our research in the department. And I think that that's a very legitimate request because, as Rick said when I came here in '69, way back at the beginning of the ARPANET, I was lucky enough to be immediately introduced to this new project, which by then was a sort of obscure. The internet, nobody knew what it was, but I got to work with some of the most prominent figures today, like Vint Cerf, Steve Crocker, and so on. And I think that experience of working in a lab was important for me, and I think all of you as engineers should have that. In fact, actually, in the fourth quarter, a student, a freshman, came to see me, and we were talking about his career goals and so on, and he said, well, I really would like to get involved in research. I said, well, but you're just a freshman. I mean, you have to take so many courses, you have no time. He insisted. I said, well, he said, I cannot wait until the third year to take all of these research courses. I said, okay. Then I brought it to my lab, and so he's now working together side by side with some of my PhD students. And I think that we are making now this involvement of undergraduate students with research labs a priority. So we have capstone courses in our program where students work on embedded systems, software engineering projects. Some of them also work on mobile wireless applications. And when they graduate, some of them tell me that the best experience they had was the one they got through these hands-on courses. And I think motivated by that, and now that the inspired leadership of Dean Wessel, we plan to introduce a freshman course, the 96. I'm surprised you mentioned it because that's to his credit. So we are going to bring together freshmen. We give them maybe Raspberry Pis or other devices, and they'll form teams, and some teams will be even coming from different departments like computer scientists, EE, mechanical engineers. So, and they'll get this first engineering experience through the first quarter of their experience here at UCLA. So we'll be monitoring that with attention. So to conclude, you see here all these beautiful projects that are available for you, areas available for you to become involved through upper courses, and in particular through perhaps some contacts with the actual researchers. And I'll be happy to elaborate on some of these opportunities with you if you come to the computer science lunch. I'll be waiting to see you there. Thank you very much.
Thank you, Mario. Wow, he brought up two things that are really close to my heart. First of all, he mentioned that he's a faculty advisor for undergraduates as well as the chair. So you should know that all of our faculty are faculty advisors to undergraduates, and every faculty member sets aside a special 3-hour time slot each quarter where they meet with undergraduates, not about the classes, but just to give them advice. And we're just coming to the end of that process. Every undergraduate student must meet with their faculty advisor at least once a year. And that has, a lot of times they're helping them get an internship, helping them figure out whether to go to graduate school, what they need to do to go to graduate school, which specialization they should do within the major. It's a really great experience. In addition to that, all undergraduate students have a peer tutor, an upperclassman that's available to them, and they have some events to meet with them, mostly during the fall, but they're always there if you want to ask a question to them. And yes, we do have Engineering 96. Next, for you guys coming here as freshmen, we have this course. There'll be offerings of it all 3 quarters, and you'll do a hands-on design project that a freshman can do. And in the pilots that we had last year, the students who took this class had a ball. So we're really excited about all that. But we've got a lot of work to do here. Let's keep moving. Remember when Al Gore took credit for the internet? You know that you are doing really well when politicians take credit for your work. So it was back in 1998, the 102nd Congress claimed wireless sensor networks as one of their greatest accomplishments. And those wireless sensor networks were actually developed by Greg Potty and Bill Kaiser. And I would say, looking back on it now, we can see that that was the beginning of the Internet of Things. This was really great work that Greg did. But Greg he's a fantastic researcher, but so much more than that. He is dedicated to the educational experience of our students. He pioneered our tech camp, which we run every summer now to bring high school students onto our campus to do projects that are designed by undergraduate mentors. And he just came on as chair of the electrical engineering department. Well, I guess it's not just anymore. So he's been chair of the electrical engineering department for about a year now. And his chairmanship is focused on the undergraduate experience. He's really doing a lot of wonderful things, including special programs and courses to improve the experience of undergraduate students. So, Greg.
Well, thanks, Rick. And as many of you know, having something be called a great accomplishment by Congress is a pretty low bar, given they can barely pass a budget. So I'd like to key off a couple of things my colleagues have said already. You've seen things already like intelligence embedded in the infrastructure, talk of autonomous vehicles, talk of the cell phone. In all of these, there is an interdisciplinary requirement for getting any of this stuff accomplished. Engineering is indeed a team sport, as Dean Wessels said in the video, and the origin of this school actually is unique in that engineering had no departments. It was viewed as a cross-disciplinary type of endeavor. Now, we do departments because that's a good way to organize the teaching program, but our research is increasingly interdisciplinary, and that's a focus of our new dean. A lot of these new hires that she's going to have happen are specifically in areas that cross departments, such as having cyber-physical systems, big data, our interactions with the medical school. So while I'm going to brag about what we do in electrical engineering, it should be taken from the view that, in fact, we are one school doing these things together. So what do EEs do? Well, I was at a recent department heads conference where they said, electrical engineers do the things that are invisible to everyone. So that's not great advertising. But you could paraphrase the Intel thing and say it's EE inside. And that's actually a big part of what we do. If you think about what goes on in the cell phone, you have sensors, you have audio interfaces, you have signal processing so it recognizes what you're telling it. It has integrated circuits. All of these are things that electrical engineers are involved in, as well as the complete optimization of this structure. Electrical engineering is an incredibly broad discipline that goes from basic applied physics in creating new devices, so new modes of computation, not just CMOS, but graphene devices. How do we manipulate light waves for photonic devices, such as the things that are involved in global telecommunications networks that now almost exclusively use optical fiber? How do we move on to do the signal processing that makes use of the large-scale integration of chips so that we can make inferences about the real world. And how do we apply these to the real world? My own research now is involved in so-called wireless health, where we use wearable devices to infer the state of how patients are actually doing things. To give a small example, I collaborate with doctors in the Department of Neurology who are interested in how patients do after a stroke. And usually they give them exercises, and when the patients come back to the doctor and the doctor asks, well, did you do these exercises? The patient nods her head and says, yes. And the doctor shakes his head and said, no. Right? It's kind of like when I did piano lessons and Mrs. McGugan asked me, did you do your scales? I said, yes, because I'd done them just before the lesson. Right? And so what we can now enable is actually objectively measuring the activities of the patients at home, see if therapies are actually effective, and by this, tune them to the needs of the individual patients. This is just another example of the interdisciplinary nature of engineering. So to conclude, many of you might, getting to engineering itself is not so easy. When I was a high school student, I had no idea what it was. I was thinking of going to physics or history or whatever. And I asked one of my lab mates who was going to do engineering what it was. And he gave an answer, and it sounded pretty good. So I got home and asked my father, and turns out I have an uncle who's an engineer. And my father, when I asked him what engineering was, he said, engineers are the builders of the world. And I thought, that sounds great. So, and many of you, in thinking about engineering, what you want to do is build cool stuff. I just want to say there's lots of opportunities to do that at UCLA. Please join us and make it happen.
Thank you, Greg. I just want to mention that in the electrical engineering department, in addition to an Engineering 96 class that you can take as a freshman, you can participate in this wonderful program that's put on by their student club called IEEE Ops. And the way IEEE Ops works is you buy this kit for $100, and there are 7 or 9 projects that you can build during the course of the year with a lot of help from the upperclassmen that are in this club. It's all a lot of fun, and you can do it as soon as you walk in the door as a freshman. And if you stick with it and build all the projects, they give you the $100 back. So it's a lot of fun, and you can start building things right away. So, all right, we've got to keep going. So materials science. So Professor Kodembaka is the vice chair for undergraduate students in the materials science department. And he does in situ microscopy of materials at nanoscale using scanning tunneling microscopes, specifically two-dimensional materials and tough ceramics. And so I asked Sunil, okay, so how can I break it down for people? And he says, just tell them I do reality TV for materials. So here is Professor Kodembaka.
Thank you, Rick. Good morning. On behalf of the Material Science Department, welcome and congratulations to all of you for getting into UCLA. And to reiterate what Dean Jayati Murthy said, congratulations to you all the parents. I know how proud, happy, and excited you must be. I'm here to talk to you about material science engineering and try to convince those of you that are undecided to join our program and tell you how great our program is. But then after listening to all of my colleagues tell you how great their program is, I realized that there's no way that I can compete with them and tell you the latest and greatest about materials because they've already told you how best the materials can be used in a variety of applications. So instead, let me take a few minutes and answer a couple of basic questions that you might have about material science and engineering. For example, who is a material science engineer? Well, let me answer it this way. Think of a great master chef. If you're a really good cook, you know what ingredients to use, how much to use, when to use, what temperature to bake, and how long to bake if you want to make really tasty, well-textured bread, for example. So material science engineer is like a chef who knows his or her materials, what materials to be used for a given application, and how to process them to extract the best performance of these materials. Well, then you might be wondering, well, I don't need to be a chef to be eating the bread. True. So then why do material science engineering? My answer to you, short answer, is why not? Everything is materials. As Madonna said, it's materials world. But let me explain. Let me explain. Let's say that you want to work for SpaceX and build the next best, lightest, fastest, and most economical space shuttle. Then maybe you need the next generation carbon composites, or maybe carbon nanotubes, or advanced ceramics that are high temperature, ductile, and that can endure extreme environments. Or maybe you want to work for Tesla and build the next energy efficient green car. Then you need lightweight, high strength alloys, or maybe tough plastics, and you will also need the long-lasting, high-performance, high-efficiency batteries that are better than lithium-ion batteries that are there currently. Or maybe, as Professor John Stewart said, you want to build or work for Portland Cement or compete with Portland Cement to provide cement-free, green, energy-efficient housing. Then maybe you need geopolymers or other alternative materials that are at least as good as cement or better than existing cement. Or as Professor Liao said, maybe you want to work with biomaterials, biomedical implants, next generation prosthetic limbs, pacemakers, or dental fillings. Then you need advanced materials that are smart, self-preserving, self-healing, and also biocompatible. Or maybe you want to build the next energy-efficient catalyst, fuel cells, or pharmaceuticals. Then you need new materials. Or maybe you want to build the next generation supercomputer that's portable, or next electronic gadget, or a next Google phone or Google Glass, Apple TV. Whatever it is, then you would need high-performance semiconductors and advanced nanoscale materials that can be integrated into the new electronic circuitry. So you see, basically, whether you want to control the spin of an electron, or the weight of a car or an airplane, or the greenness of a battery or the next generation energy harvesting device, you need materials, materials, materials. And you need someone who understands the behavior of materials and who can engineer these materials to achieve the needs, the performance that you need. So finally, let me conclude by this. What else can a material science engineer do? Well, you can become the next CEO of Google or be like me. Thank you and welcome to UCLA.
Thank you, Sunil. All right, and our last department for today is the Department of Mechanical and Aerospace Engineering, and its chair is Professor T.C. Sal. Fitting for someone who controls a large department, Professor Sal studies control theory. One area where he's made a large impact is the control of manufacturing processes for automobile engines. By using control theory to enable pistons to be manufactured more quickly and more precisely so that they fit into the cylinder, with such precision that it improves the fuel efficiency. Basically, Professor Sal has improved the fuel efficiency and lowered the cost of many of the cars that are on the road today. So here's Professor Sal.
It's really hard to be the last speaker. But first, I want to say our department, Mechanical and Aerospace Engineering Department, is all of the above. All right. So let me elaborate a little bit. Can you go to the next? Because if you look at these pictures, okay, these slides, yes. You have heard about putting device like camera into bloodstreams or gut. That's the picture you see on the left there. Okay. And there's space exploration. How do we do propulsion? Plasmas that create propulsion to do space exploration. That's on the right there, lower corner there. And then how do you create device, machine that interact with people, the robots? That's what you see there, so that they can share ice cream. And so it's just the visuals here. So what is mechanical and aerospace engineering? for all disciplines, all engineering disciplines, and especially with your experience in high school education, you are interested in engineering because of math and science. So math and science is the core of our discipline, including every engineering discipline. And in engineering, we take math and science to become solving problems. And so engineering is about solving problems. And what kind of problems do we solve? Maybe we can talk about what mechanical and aerospace engineers aspire to or are inspired by things that they see. I would say everything that involves movements of changes, that sort of inspire students and faculties who are interested in mechanical and aerospace engineering. So for example, vehicles, whether it's ground vehicles, aircraft, spacecraft, or underwater vehicles, robots, right? And those are very visible, so we are not like double E is something inside, we are very visible. And maybe there's something that's not so visible, but you can feel is the flow. Maybe it's a flow of temperature difference, heat flow, or it's air flow, and that are also very much to the heart of mechanical and aerospace engineering. So you can see there's a list of topics that's listed there, that's major research areas of our faculty. And of course, being in UCLA, our department faculty is just like other faculties in other departments, that we work on very interdisciplinary type of research. And virtually, actually, our department, either faculty has, I would safely say that our faculty has joint appointment with virtually every other engineering department, or we are working on projects, research with other departments and also beyond engineering departments like medical schools. So for example, for myself, the math I work on to solve a very precise engine piston machining is now used to apply to research on machining eyes lens for cataract surgery, robotic cataract surgery. So that's a great thing. You learn math and science, you learn engineering skills to solve problems, and you can solve all kinds of problems with the basic same principle. So our department has has two disciplines, two majors, mechanical engineering and aerospace engineering. Mechanical engineering tends to be very broad, like I said, and aerospace engineering is a little bit more focused, more on vehicles, aircraft and spacecraft, and the technology required for, I would say, fight gravity, right? Okay. And our department consists of 36 faculty members and about 700 undergrad students and about 300 graduate students. So I think this is an important number to realize, about 36, 700, 300. Why do I think this is important? I think UCLA Engineering, or staff from our department and engineering and UCLA, is actually kind of unique in this sense. If you look at the size of our department compared to other schools, or if you think of engineering, let's just lump our department or engineering, you can think around the same way. We are small or smaller compared to other state schools, public engineering schools. We are about the same size with elite private schools. But we are within UCLA, which is a large, general, comprehensive universities. So I have visited many other schools and bring my children to visit many other schools. I always felt that UCLA is very unique, my department and engineering is very unique in UCLA in the sense that we actually have the advantage of being smaller department and schools that have private school fields and community in a large, comprehensive university that have a lot of opportunities. And with that, I would say, isn't that a great sales pitch to you? And I would like you to seriously consider that, because I really feel that that's the edge of UCLA Engineering. Thank you.
Okay, so you've made it through our whirlwind tour of what engineering is here at UCLA. So we really hope that you'll join us to help build the world. And I'd like to just for a minute talk about how if you come here, you're going to help build a community. So UCLA Engineering is a community, and it functions really well in large part because of what the students do each year to create that community. We have over 45 clubs. They're extremely active. And when you come in, you'll have a peer mentor right away, an upperclassman who will help you find your way through UCLA Engineering. And that peer mentor has a secret mission, which is to get you into a club your freshman year. We want you to come into a club, join a club as a freshman. And then, as a sophomore, take on a little position in that club, be a part of a project, build something awesome, be an officer your junior year, and senior year, be president. Create a new club. A lot of our clubs win national awards. The Bioengineering Club has won the National Bioengineering Olympiad like 2 or 3 years in a row, and it's similar for the other clubs. The Electrical Engineering Club, IEEE, is regularly named a national, one of the national best chapters. And this is, it's part of who we are, and and when you join that club, you'll make a group of friends that will help you. They'll be with you through your whole experience of the university. So with that, actually, we're running a little bit behind, so we're just going to bring this session to a close, and you're going to go to your departmental session. And I want to explain how that's going to happen. So you don't have to find your way across campus to the correct building for the next session. All you have to do is walk out into the courtyard, and don't stop immediately at the door because people will then walk over top of you. So walk into the courtyard, know that there are people behind you, and then look around for the big banner, and you're about to meet that community because there'll be a banner held up by some of our students with the name of your major on it. Go to the banner, and then they will lead you to the room for the departmental sessions. So with that, we've really enjoyed getting this chance to talk to you. This is a very special day for us, and we hope that you discover what UCLA Engineering really is and make that right choice. Thank you.